Hi everyone, my name is Zhan Jiang. I'm currently a student at the University of Michigan. My advisor is Mel Hoxter, and I study communal algebra and algebra geometry. My research are about closure theories, multiplicities, and singularities. A lot of topics I study are related to a series of conjectures called homological conjectures. Here is a very nice diagram. I want you to pay attention to the top three boxes. The first box saying a good closure theory, the second saying weakly functorial big Cohen-Macaulay algebras, and the third saying small Cohen-Macaulay algebras. I want to say that these three are more or less the most important three among all conjectures, as the three implies the rest of them. My first research project is related to the first box I just talked about, namely a good closure theory. So to begin, let me tell you a little bit of history here. Riemann-Heitmann defined four closure operations in mixed characteristic in order to generalize tight closure. Recently, he and Marr showed that the EPF closure satisfies so-called usual colon capture, which is a very nice property. Jeffrey Dietz, on the other hand, took a different approach to generalize tight closure. He defined 7 axioms to characterize a good closure operation. He shows that the equivalence between the existence of big Macaulay module and the existence of a Dietz closure, namely a closure satisfying all his axioms. Later, Rebecca R.G. added one axiom to the set of axioms, and she proved that the existence of Baker-Macaulay algebra is equivalent to the existence of a Dietz closure satisfying the algebra axiom. What I did in this area is that I defined a new closure operation called WEPF, and I was able to show that WEPF is a Dietz closure satisfying the algebra axiom. This is the first known example of a Dietz closure in mixed characteristic. But I also want to point out that the same technique can be used to prove R1F closure, which was defined by Heitmann, is also a Dietz closure. I also proved a lot of related results. As for future directions, I really want to continue to study the relationship between all these closure operations. I also want to develop a test element theory for all these closure operations. My second project concerns the tight closure notion in equal characteristic zero defined by Hoxter and Huneke. The theory they develop is useful and beautiful. Inside this gorgeous framework, there is a lot to explore, especially for tight closure for huge algebras, for example, semi-analytic algebras. The definition of tight closure in equal characteristic zero is a bit of technique. They used a notion called descent, which may take a very long time to explain the detail. And my main contribution here is that I proved some new results in characteristic P relating the complete Jacobian ideal and the test elements. I also use Artin-Rota's theorem to show that in equal characteristic zero, the elements in the complete Jacobian ideal multiplies the tight closure of an ideal back into the ideal itself. As for future directions, I will want to continue to explore the usage of Artin-Rota's theorem, as the theorem holds in any characteristic. I also want to point out that Jeffrey Dietz and Rebecca R.G. used the notion of ultra products to prove a lot of results about Baker-Macaulay algebras in equal characteristic zero. So there are also a lot of interesting questions in that direction to explore. My third project is very fun. It's about a new numerical invariant called size. This notion is based on a notion developed by Hoxter and Huneke called quasi-length. They developed quasi-length to define heuristic measures for top local homology modules. The definition is a little bit technical, and I listed here for you to read. The main contribution for me is that I use this notion to define size, and I showed that the size is always bounded between the height and the arithmetic rank of an ideal. I also showed that size equal to the height in certain low-dimensional cases. One annoying property about quasi-length is that it fails the additive property. Therefore, I also studied some cases where the additive property of quasi-length fails. For future directions in this subject, I want to continue to study when the size equals to the height of an ideal. Also, the size bounded the arithmetic rank from below. Therefore, one may use size to attack set theoretical intersection problems. Finally, I want to point out that one can use symbolic powers to calculate the size under multiple assumptions. The consequence of this calculation is yet to be further explored. Thank you all for listening. That's all about my research and about me. If you have any questions or comments, feel free to contact me via my email.